A system model with an absorbing state is defined over a standard probability space extended by a cemetery state. The state space is augmented. The process takes values in the union of the live operating region and the absorbing state delta. The absorbing state is a formal element of the state space, not an external failure category. Once the trajectory enters delta, it remains there permanently. This is encoded in the transition law, not as a side condition. The formal structure of the absorbing state is a prerequisite for correctly formulating both absorption and conditioning in system architecture. The stopping time formalizes the first entry into the absorbing failure state. Before the stopping time, the system evolves under its full live dynamics. The transition law applies without restriction. At the stopping time, the trajectory transitions permanently to the absorbing state. The absorption event is path level. It occurs or does not occur on each individual trajectory. Computing the distribution of the stopping time requires integrating the live transition law over all trajectories, weighted by the probability that they have not yet been absorbed by the query time. Conditioning on survival defines a change of measure on the probability space. The original measure assigns probability to all trajectories, including those that fail before time t. The conditioned measure assigns probability only to trajectories that survive through time t, normalized to integrate to 1. This change of measure is a Bayes update on the path sigma algebra. Under the conditioned measure, the system's transition rates, mean, and variance are all different from their unconditional counterparts. The conditioned measure is a genuinely distinct stochastic law, not merely a filtered version of the original. Absorption and conditioning are formally distinct operations on the system model. Absorption is a property of individual trajectories. A trajectory is absorbed when it crosses the failure boundary. Conditioning is an operation on the probability measure. It restricts attention to the sub-ensemble of trajectories satisfying a specified event. These two operations have different inputs, different outputs, and different implications for system architecture. A system design that conflates them will produce incorrect predictions of both the failure distribution and the performance characteristics of surviving systems. The non-commutation of limits and conditioning under absorption is a structural property of the system model. Taking the long-run limit of the trajectory before conditioning on survival yields the absorbing state value for absorbed trajectories. Conditioning on survival before taking the long-run limit yields the stationary distribution of the live subdynamics. These two operations do not commute because the set of trajectories involved in each computation is different. The architect must specify which computation corresponds to the design requirement, long-run behavior of the full system population, or long-run behavior of the surviving subpopulation. The canonical examples of absorption versus conditioning arise in reliability engineering and population dynamics. In reliability engineering, absorption models component failure. The component fails permanently and is no longer available. Conditioning on survival describes the conditional reliability of components that have not yet failed. In population dynamics, absorption models extinction. The lineage terminates permanently. In both cases, the structure of the formal model is identical, an absorbing state added to the state space, and a conditioning operation that restricts to the live sub-ensemble. The formal distinction between the two operations is not domain-specific. It is a general architectural principle.